Hello, I'm back again. We concluded the last segment looking at these two plots. We observed that the means in the plots are about the same, both in the neighborhood of 0.5, but that the standard deviations were quite different, and that the spread was much tighter when we flipped the coin 1,000 times per trial than when we flipped it 100 times per trial. The distribution of results in each of these plots is close to what's called a normal distribution. Just a normal distribution peaks at the mean, as we see here, and falls off symmetrically, or at least close to symmetrically, to the left and right of the mean. The shape of the normal distribution is said to resemble that of a bell, so it is sometimes referred to as the bell curve. Though I have to say, try as I might, I don't see much in common between the normal distribution and any of these bells. Scientists often refer to the normal distribution as a Gaussian distribution, in honor of the astronomer Carl Friedrich Gauss. Normal distributions are frequently used in constructing probabilistic models for at least two reasons. One, they have nice mathematical properties, as we'll see shortly. And two, even more importantly, they actually occur quite frequently in practice. Normal distributions are nice mathematically because they can be completely specified by two parameters: the mean, often written with the Greek letter mu, and the standard deviation, something we've already talked about quite a lot, often written with the Greek letter sigma. Knowing these two parameters is equivalent to knowing the entire distribution. So far we've looked at two functions from random that draw from a uniform distribution, random.choice and random.random. Now I want to look at a function that draws from a normal distribution. That function is random.Gauss. Let's look at this code. Got a function here that's going to produce a Gaussian or normal distribution. Starts with the mean and the standard deviation and some number of samples. It initializes the samples to the empty list. And then for I in range number of samples, it calls random.Gauss, which, as you might guess, takes two parameters, the mean and the standard deviation, and returns some value based from the normal distribution defined by these two parameters. Then when I'm done, I'm going to use pylab.hist to plot it. All right, let's run it and see what we get. Coming over here to the code window. I'll set the mean to 0, maybe 0.0, the same thing. The standard deviation to 1, and we'll look at 100,000 samples. Wow, it kind of does look like a bell, doesn't it? I'm sorry for my previous snarky comments. So we can see it's peaking near the mean, which we said should be 0, and then falling off almost symmetrically. Let's see if it's really symmetric. We can zoom in up here. Well, you can see it's not symmetric. If I took more samples, it would be closer to symmetric, but it's pretty close. And of course, as we zoom out again, it really does look pretty good. For normal distributions, the standard deviation can be used to produce something called a confidence interval. The basic idea is instead of estimating an unknown parameter by a single value, for example, the mean of a set of trials, a confidence interval provides a range of values that is likely to contain the unknown value and a confidence level that speaks to the question of how certain are we that the unknown lies within the range or the interval. For example, a political poll, and as I record this, the US is buried in political polls, might indicate that a candidate is likely to get, say, 52% of the vote, plus or minus 4%. And typically, even though it's not always stated explicitly, when people don't state the level, they typically mean a 95% confidence level. So what this would mean is that the pollster believes that with a probability of 0.95, the candidate will receive somewhere between 48 and 56% of the votes. Together, the confidence interval and the confidence level indicate the reliability of an estimate. As you can imagine, it's almost always the case that increasing the confidence level will widen the confidence interval. If you think about it, it makes a lot of sense. If I want to be 99% confident that my unknown lies within the interval, then I probably need a bigger interval than if I only wanted to be, say, 50% confident. Keep in mind that the calculation of a confidence interval requires assumptions about the nature of the space being sampled. Most typically, it assumes that the distribution of errors of estimation is normal. The empirical rule for normal distributions provides a handy way to estimate confidence intervals and levels given the mean and standard deviation. For example, approximately 68% of the data, and I say approximately, falls within one standard deviation of the mean, again, for a normal distribution. Roughly 95% of the data falls within two standard deviations of the mean, and almost all, roughly 99.7% of the data, will fall within three standard deviations of the mean. Well, this provides us an interesting and useful way to think about, say, polling data under the assumption that the errors are normally distributed. Provides us a useful way to think about, quiz scores, assuming that the scores in the quiz are normally distributed. But there's a difference between those two. When we think about quiz scores, we actually have ground truth. We can plot all of the quizzes for 600x and compute the mean and the standard deviation. And we know that it's exactly right because we're not sampling. But pollsters are sampling. They don't have ground truth. So what do? Well, you could imagine that maybe they run many different polls, take the average of the polls, look at the standard deviation, and reach a conclusion that way. And indeed, some people do that by aggregating polls. But typically for an individual pollster, that's way too expensive. So they instead conduct a single poll and rely on something called the standard error. The standard error provides an estimate of the standard deviation. It works under the assumption that errors are normally distributed and that the sampled population is small relative to the actual population. It can be estimated from a percentage P, that's the percentage of the population that's being sampled, and the actual sample size, N. So the standard error is defined by the following rather simple equation. P, the percentage sampled, times 100 minus N, so you can think of that as percentage not sampled, divided by N, and then all of that to the half power, or the square root.